look at the first set of examples for our Fourier transform. Rewinding the notation, we talk about Fourier transform of a function f. We define it as the integral from minus infinity to plus infinity of fx times e at the minus omega x dx, and the inverse Fourier transform of f hat is equal to 1 over 2 pi integral between minus infinity and plus infinity of f hat omega e at the I omega x d omega. So you notice how going from f to the Fourier transform of f, we have an exponential of minus I omega x, and we are integrating over x. And to come back, we have an integral over, we have a complex exponential of e of I omega x. So it looks very similar, but now we are integrating over omega. We often use a shorthand notation of Fourier transform f being f hat. As we will go through this topic, you will notice that there are really a lot of similarity, at least conceptually, with the Laplace transform. So all the approaches we have developed for the Laplace transform do work for the Fourier transform with a little bit of care of the translation between the two. As first example, we can look at the Heaviside function, the function that it's 0 before 0 and 1 after 0. We want to do the difference between two Heaviside functions shifted at plus 1 and minus 1. So we're looking at a function that is 0 for absolute value of x bigger than 1, so under minus 1 and over plus 1, and 1 between minus 1 and plus 1. Then we want to do the Fourier transform of this step function, so a function that is just non-zero between minus 1 and 1. So obviously the infinite integral that we have just rescales to an integral between minus 1 and 1 of the complex exponential that we can solve quite easily, remembering that, well, the derivatives of the exponential are quite easy. So we're just gaining 1 over I omega with a minus in front. So by going through all the steps, we recover a difference, a constant depending on I omega, and a difference between exponential of minus I omega and exponential of I omega. You can either do the Euler formula for both, or remember that this is the definition of the sine of omega. So the Fourier transform of this step function that is non-zero between minus 1 and 1 is 2 sine omega over omega. So we went from a function defined over x to a function defined on omega. Omega is the kind of variable that can go from minus infinity to plus infinity. Notice that we went from a function that is local, that gives us information only between minus 1 and plus 1 and everywhere else is 0, to a function that is non-local, is the sign that is rescaled to tend to 0, but it's still a non-local information. This is going to be fairly normal in Fourier transforms, that we're going from local to non-local or from non-local to local information. And this is one of the interesting tricks that you can apply when looking at Fourier transform. One side is usually much easier than the other. And that's what we are trying to exploit as best as possible. Let's look at another example. This is the Heaviside function multiplied by a real exponential. The exponent is minus ax, and we want this to be decaying, otherwise we cannot apply the Fourier transform, so we need the coefficient a to be strictly positive. By the multiplication with the Heaviside function, it means that for x smaller than 0, we're looking at 0, and for x bigger than 0, we're looking at a negative exponential. And we want to compute f hat, so the Fourier transform. This is by definition the integral from minus infinity to plus infinity of f of x exponential of minus I omega x dx. We're looking at x, and sometimes we will be talking about the real space when we're looking at functions of x. And omega, or sometimes using k, is called the frequency space or the Fourier space. So let's try to have it a go at computing this function. Well, our starting function f of x is 0 for x negative, so we can throw away half of the integral. We only have to compute the integral from 0 to plus infinity of the product of two exponentials. The product of two exponential is the exponential of the sum of the two exponents. So we have x appearing just once in one of the exponents. So we remember how the integral of exponentials work. And our f hat is 1 over a, that is the rescaling of our exponential, plus I omega. Notice that this is a complex result. So omega, you have to think about it as a real variable. So I omega is always complex. And a fraction with a denominator that is complex is also something complex. So we went from having a real function that is an exponential, a bounded exponential, to in real space, to a complex function in frequency space. This is fairly normal. Actually, it holds that the Fourier transform of a function is real only if the function f has this property that f of x is equal to f of minus x for all x. Or we say that f is even. If f is not even, then the Fourier transform of f is going to be complex. And you can check it because we were looking at the step function between minus 1 and 1 that had a real Fourier transform, and now that we're looking at something that is not symmetric on the two sides, that is not even, then we have a complex result. This is true in general.